So what's a vector? Well, in this video, I'll be going over vectors and how to use them and what they look like, adding them, subtracting them, multiplying them, and yeah. So a vector can be written as x comma y with these two components. And these two components help with the graphing of a vector. So what does a vector look like on a graph? Well, it looks like this. One thing to note is that the tail, or where the vector starts, that doesn't really matter, meaning this vector is the same as this vector drawn, which is the same as this vector, assuming that all these vectors are parallel and they're all the same length. So that's the most important part. So what are these x and y components? What purpose do those serve? Well, just in regular graphing, right, we have the x component being this component, the y component being this. And that's exactly what a vector has. This is the x component and the y component. So how do we use this? How do we find the length of the vector? How do we find the angle? How do we do all that? What are the different ways to write vectors? So I'll go over the second way to write a vector. Second way to write a vector is, or direction and magnitude, but you basically have the magnitude, we'll just call this r. You have r comma theta, where this is theta. And this looks very similar to polar form, where you're given the radius and the angle. But for vectors, it's the same thing. How do we find r? I'm pretty sure you guys are familiar with Pythagorean theorem. So we just have x squared plus y squared is r squared. So r is equal to square root of x squared plus y squared. And then how do we find theta? We know our trig properties. We know that tangent theta is equal to opposite over adjacent, or y over x. So theta is equal to inverse tan of y over x. So we know how to write vectors in these two forms now. But what does it mean to add vectors? So I'll draw a graph here. And say I have this vector here, and I want to add it with this vector here. You might be thinking, these are two different vectors, they have nothing to do with each other. How do we add them? Well, remember, the tail, I'll do this in white, the tail does not matter, meaning it does not matter where the tail is. So what if we just move this vector onto the red vector here? It has the same magnitude, it has the same direction as this other yellow vector, but it's just attached to the tip of this red vector. So what does it mean to add vectors? Just get rid of this line because it kind of looks like a vector. So to add vectors, it's just this vector right here. Now, how do we do this algebraically? Well, we'll go back to our vector example here. Here's our red vector. Here's our yellow vector. And our sum vector is right here, the sum of our vectors. So this looks like around, maybe we could say 5, 3, this red vector. I'll actually do this in red. This vector looks like 5, 3. This yellow vector looks like maybe -3, 4. That looks close enough for our purpose. So to add vectors, well, what do we see here? We have 5, 3, and looks like since this is the height here, this is the height of the yellow vector, I guess we could just add the heights here, right? so that means our y component would be 7. And for x, we have our x here, and we're just adding our x component here. So I guess we just add the x components, we get 2. So this is our resultant vector, or resultant vector. And this looks about right. 2 over 7 up, that looks about right. Now what does it mean to subtract vectors? I'll draw the same graph. So I have a vector here, and I want to subtract it with, say, the vector here maybe. Well, we know that adding this vector and this vector gives us this green vector. I'll actually just do this in red. Adding the red vector and the yellow vector gives us the green vector. Right, so I'll just do green is equal to yellow plus red. Now we want to solve for whatever yellow is, right? We want to solve for this. So that's how we subtract vectors. Green minus red is equal to yellow. And this is what subtracting the vectors green and red mean. Just finding this yellow vector right here. Now multiplying vectors is a bit different and somewhat hard to graph. But here, there are two ways to do it. There's something called the dot product, and there's something called the cross product. For this video, I'll just be focusing on the dot product, and then when we get deeper into matrices and vectors, I'll be going over the cross product. So you can treat the dot product as a function. It's just a, some vector a, times, or dot, some vector b, is equal to, it's actually a scalar, c. A scalar just means a number. So how does this work? We can break down a into components x, y, and b into components x1, y1. C would just be x times x1 plus y times y1. So this is our scalar. This is how you find the dot product between a and b. But I don't really see a use for this. Maybe there's a different way to express dot product, and you're going to be 100% right. So the dot product of a and b, do this in yellow, a times b can be also written as the magnitude of a times the magnitude of b times cosine theta, where theta is the angle between vectors a and b. This I'll graph to make a bit more easier. So we have vector a, I'll do this in a different color. Vector a, we have vector b, and then we know that this is theta, and this is the length of b, this is the length of a, the magnitude of a. So finding the dot product, we'll just be multiplying this magnitude of a times this magnitude of b times cosine the angle between vectors a and b. This seems a little bit more useful. So what if I was given the, I'll just keep this up here actually. What if I was given the problem, find the angle between vectors, let's say 1, 2, and let's say -1, 3. So let's draw a graph, make it easier to visualize. We have a vector 1, 2, so that's about here, and a vector -1, 3, so -1, 3, maybe somewhere here. So our theta, what we're trying to find would be right here. And yeah, so we could use both of our ways now, both of our formulas to find the dot product. First, let's just rearrange this. We'll just solve for cosine theta, or just solve for theta. We have a times b over magnitude a times magnitude of b. The inverse cosine of all of that is equal to theta, and we want to find theta. So in this case, what's the magnitude of a? This should just be root 5. Magnitude of b should just be root 10. Now we need to find the dot product of a and b. Well, we have it right here. This is a very easy way to find the dot product without the angle, without magnitude, without all that stuff. So we know the components, so we could just find the dot product. This would be negative 1. 1 times negative 1 is negative 1. Plus 2 times 3 is 6, which is equal to 5. So the dot product is 5, which is, sorry, I'll just put dot product. And then we can plug all this information into here. So we have inverse cosine a times b, dot product of a and b, which we know is 5, over magnitude of a times magnitude of b, which is root 50. This could also be simplified to inverse cosine 5 over 5 root 2, or just inverse cosine root 2 over 2. Well, wait a minute. We know exactly what inverse cosine root 2 over 2 is, right? We just know that this could be pi over 4. That's the angle between these two vectors. So this would be our answer. As you can see, we basically just isolated theta, just solving for theta given this information. We utilized this dot product formula to calculate this dot product, and then we made theta really easy to find by finding the magnitudes of these two vectors. Thus, we're given our angle.